just put that right there. Product of G and the number of strictly increasing subsequences. I think there can only be n log n G's. I'll think about this one. Less than, greater than. So the idea is any ijk where a at I is greater than a at j is greater than a at k. So I just need to use a monotonic stack for that. To be like for any j where it's the nearest I and k. So stack dot in place while I think I'm going to have these be in the same, because I'm going to be referencing them next to each other every single time. While not stack dot empty and stack dot back dot first. I want the nearest thing after it that's less than it. So the monotonic stack is going to be monotonically decreasing, which means if I add something, I want to pop off as long as it's less than x. So y and j is equal to stack.top. Okay. B at I at 0 equals j. B at j of 1 equals I. And then I think you just instantiate it to b at I at 0 equals -1, I think. B at I at 1 equals n. Okay, so it's saying nothing is to the left of the first element and less than it. Also, I guess nothing is to the right of the first element. Or no, nothing is to the left of the first element and greater than it. Also, it seems like nothing is to the right of the first element and less than it. Which is true because it's 1. So it's the smallest element. This is saying nothing is to the right and less than a 5, which is true. And index 2 is the nearest thing to the right and less than it. Okay, that's good. Now I have that. I don't even really need A at I. I think I can just say like, I think I barely even need, no, yeah, that's fine. I don't even need A. I could just use the stack itself, but whatever. For int I equals n minus 1, I is greater than or equal to 0, I minus minus. So now I'm going to take a prefix sum backwards and say, for every interval, for every left and right interval that every index contains of the first thing to the left of it that's greater than it, and the first thing to the right of it that's smaller than it, like that's going to form a triplet that's descending, and that's what I care about, where g of b and f of b are going to be different, or in my case of a. And so for every left bound, I need to find the earliest right bound. And this is just me blatantly having looked at the hints and stuff. Auto LR equals B at I. What am I doing here? So I'm going to say, okay, now when you're at the left interval, you could use this to get to your right interval. So I think what I'm going to do is just say something like, I think I'm using C for this, yeah. So if L doesn't equal -1, C at L is equal to min of C at L and R. And then I kind of need to like instantiate C. So I guess up here I could just also say like C at I equals N. Okay, but now it's saying you could just jump discretely from any left to any right, but I want to take like kind of a prefix minimum going backwards. That's like the whole point of this. So I guess if I is less than n minus 1, pretty bad to have an if statement that I know is going to be false the first time and true every other time, but I think the way that the compiler is going to optimize, like with the hits and misses, I think it won't really matter. I think it'll still be like 80-90% hit rate. C, no, that's not smart. Because I'm changing at L. And I know L will always be less than I. I guess I could do that, but that's kind of weird. For int I is equal to n minus 2, I is greater than or equal to 0, I minus minus, C at I equals min C at I plus 1. Okay, and now for every query, what am I doing? I'm just showing if it's true or false. So I need at least a single element that has this left bound or above with a right bound of before R. So I'm going to say input L, input R, and then res dot in place back C at L is less than or equal to R. That checks out. No, yes, 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 no, no, yes, no. I think that's exactly backwards. So how did that happen? That happened because this is saying it is included. If it is included, that means G does optimize, but I want to say that G doesn't optimize if I'm trying to say that F of B and G of B are the same. Yes, no, 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 yes, yes, no, yes, yes. Okay. Let's just grab some of these. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, doesn't matter. It's like at least 20. Yeah, that looks pretty good. Shit. Did I make it farther? Yeah, I made it a little bit farther. Okay, all these are right. All those are right. So at least up to like the 15th test case, it's fine. Damn. So exactly right here, it says yes when the answer should be no. Which might just be the test cases being weird. Yeah, I think it is. No. Maybe not. If I said it's 1,000, do I just get like a million S's? Yeses? Yeah, I do. Okay, it is that. Yes, yes, no, no, yes, no, yes. And then a bunch of no's where mine says yes, yes. Okay, the left bound is -1. The right bound is n. For every element, shouldn't it be, well, it's less than x? Yeah, why would it not be that? stack.top.first is less than x. Okay, I think it's that I don't want to say this here. Be a j at 1 equals I. -1, 1. I can't handle that. I need it to be condensed. Okay, so that makes sense. It's saying nothing is to the left of this and greater than it. No, but now it's saying this is to the right of it and less than it, which is not true. So I'm not sure why, but I guess I did want this to be greater than. If it's greater than, I'm saying yeah, okay. Everything to the left of you that's greater than you this is the first thing to the right of that and less than it. But I don't think I'm just setting I repeatedly. I think I'm saying I kind of want to say like if this and then while this. I think like that. And I think it just happens to have not mattered for the initial test case. Yes, no, 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 yes, yes, no, no, no. That's not right. Wait, that's not right for multiple reasons. Yes, no, 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 yes, yes, no, 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 yeah. While the thing to the left of this is greater than it, for all of those, they point to I. It should definitely be second, not first. It's probably part of the problem. Yes, no, 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 yes, yes, no, yes, yes. All right, let's see how that does. It was pointing to the last thing greater than it, or the earliest thing greater than it, but I wanted it to point to the most recent thing greater than it. Damn it. that make it any further? No, it didn't. Okay, but that's like, at least there's stuff to look at. So if there's something on the stack that's greater than this element, this points to the first one, while there's something on the stack. It points to this, and then it's concluded. Okay. Left and right is B at I. Is there any world where this fucks it up? No, I don't think so. For L and R and B at I, if L isn't -1, then there's something before this that's greater than it. So C at L is min of C at L and R, which could be the end of the array, which would mean there's nothing. For every element, take the reverse prefix minimum. Okay, get the L and R, say if it's possible or not. That seems right. Whoa. -1 and 5. There's nothing before it, nothing after it. Nothing before it. The second index is after it. Okay, 1, 3, 2, 4, 3, 5. That all makes sense. Now for 3, 2, 1, 4, 5, it's saying nothing before it that works. This is its right bound. For the 2, it's saying 0 to 2. For this, it's saying the 2 is the first thing, but there's nothing after it. Okay, there's nothing before this, and nothing after it. There's nothing before this, and nothing after it. So it's monotonically increasing. No, surely you're able to see the 29th test case from this, or 29th yes and no. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Yeah, there's at least 25 test cases. For real? That's weird. Okay. 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 2. Okay, 2, 1, 3, 1, 3, 1. Three, 1. Three, 1. I think it's up to 8. I'm gonna start over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Damn, really? That's very unfortunate. I just barely can't see it. It's probably on purpose. Okay, would expected a no, it found a yes. So that means I'm unduly saying that g of x can optimize over f of x when it can't. And in that world, that means C at L is greater than R. Or no, I'm trying to figure out when they're the same. Yeah. Okay, good. Okay, so they're this. I'm saying that they're the same when they're not. So g of x could have worked could have taken less operations than f of x. So that means that my intervals are too small, or I'm not checking them properly or something. I'm guessing it's a subarray inclusive. Yeah. Is it a problem with a default? Am I not setting everything in default? I'm saying c at I equals n. C is not being set here, so I can at least do that. B at I at 0, B at I at 1. That feels a little bit weird. I'd rather just have that its own thing. I doubt that changes anything. A at I just doesn't even matter. Y and J stacked on top. If L doesn't equal -1. Oh, I see. No. B at I at 0. The only place I'm ever going to change that is here. I guess one thing I could do is say it's from 1 to n minus 1. Doesn't really matter, but... Yeah. Man. Is there anything I need to do after I complete this? In a monotonic stack, sometimes it's like while the stack has anything on it. But I don't think so, because you're going to get a purely ascending stack. It's monotonically increasing, and you're saying everything in this stack at the very least has nothing after it that's less than it. Do I care about that? I don't think I care about that. As long as the stack, if the stack isn't empty, and the current largest thing you've seen so far is larger than X, you would want to say that's the nearest element to the left of this. And anything to the right of this that's larger than this is the nearest element to the right of that that's less than that. Can I always safely just take the nearest element to the left of this? So this is the nearest element to the left. This is the nearest element to the right. In theory, I'm saying g of x is less than f of x if both of these can swap over I, which means that both of them would have to be included in the subarray that's being queried. So what I can say is just for any L, go backwards and be like, okay, that's L1 and L2 and L3 and so on. So you go back and you say, what's the minimum R you've ever seen for any L after this? Because even if you include the L's out here, the minimum R will necessarily be greater than the minimum L plus 1. So those don't matter. So you go back. Oh, nice Solaris. I think I have an idea. After this one, I want to do E2. I think I have an idea for it. So you go backwards and you say, okay, take the prefix minimum of all right bounds. So maybe this left bound is like there, and this left bound is also this element, and this left bound is there. Then you would say like, okay, well, if my subarray was there, then you'd say yeah, because this is in there. And you take the prefix, so you'd say actually this only goes to there. Did you already do E1? Yeah, I was kind of proud. I did E1. I just raw dogged this thing in like an hour, or like I was like less than an hour. When you and Betsimp were talking about it on Discord, I was like, I think I have an idea for E2, so I'm going to implement E1 and then see where that goes. My idea for E1 worked, obviously, but the implementation optimization, well, I've got an idea for it, and I think I know what to do. I don't think it's the optimization that I originally thought it was. I thought you were doing the last one. Oh no, it's that other div too. It's not even harder than E1. Wait, what are you talking about? I'm working on this D right now. Oh, there's another div 2 with a 2-part E1 and E2. Ah, okay. Did you wind up doing these? Because the D of the other. Oh, interesting. Okay. Maybe I do that. I think my implementation for E2 really shouldn't take long. I think I don't even care about F. I'm not going to look at that. I might as well just do something else. Although this is a real waste of time. I've solved up to E2 on that one and up to D on the next one. What the hell am I doing here? What? It's just like, so the conundrum I'm in is that it's exactly the test case. This is the final character of the 28th yes or no, and the 29th yes or no is where they differ. So I just have no idea what the input was. I guess I can assume that it probably is one query on a length of 4 array, because that seems like what's going on here. So maybe I can just sort of make it myself. I'll say n is 4, q is 1, and the D of the last contest was so simple I was flabbergasted. I was really surprised by, I'm still below the glass ceiling. What's the glass ceiling? They get back to expert thanks to the former being unrated in the fast ABC on the ladder. Oh yeah, you said your ABC was fast. I was blown away by the last Leetcode contest. Like, what the hell was that? This was just like a typing test almost. Like, it was very weird. I think they've been like getting harder and harder and harder, and they were like, okay. Wow, I'm actually really surprised at that. I think my score said like 180 or something. This just said 168. Which is very weird. That means that of all the people in the top 200, or I guess ahead of me, like 12 people were ChatGPT cheaters. Overcomplexified Q4. Yeah, I mean, I spent so much longer on Q4 than I needed to. Like, there's obvious room for improvement for me. I got these in 9 minutes, and then this one was like 39 minutes, I think, or 35. This was like not a bad problem. This was kind of a good, as far as easy Q4s go, like, all right, this was fair. Q1 through 3, though, was like, what the fuck is going on here? I mean, I don't know. I guess fair enough, right? But this was like a nothing. This was like easy for a Q1 in my mind. This one was very easy for a Q2. This one was, you had to know what a monotonic stack was, which at this point is like very easy for a Q3. And this was like digit GP, which is like, I think as far as Leetcode is concerned, that's like pretty standard. It's not really anything crazy. No digit GP needed. Oh, interesting. Okay, you get the number of bits. And then you bit shift n by the number of bits over 2. Oh, this is just the first half, okay. Okay, yeah. Yeah, I see. I was actually kind of proud of mine. I think I overcomplicated it severely then. I was like, this is actually now that we're talking about it, kind of an interesting digit GP technique that I haven't really ever seen before, where I was like, you're kind of referencing no, not really. It's just digit GP over the like first half mirrored to the second half. Posted an explanation in Leetcode server, binary search. Interesting. That's kind of cool. So there's 3 different solutions to this. All right, I think I'm going in circles here. I don't know what the hell. This is where I just want to like Command A, Command I, what's wrong with it. But I don't really want to know what's wrong with it. Except I really do want to know what's wrong with it. It's in the contest discussion in Chi-Chi's server. I don't think I've spent any time in Chi-Chi's server. There's probably smart people in there. From 1 to n minus 1, I already changed that to be the way that it is for no real reason. If you don't have the right idea, I think it's a nightmare. You're talking about the one I'm doing right now. I feel like this should just straight up work. The idea is you got f of an array and g of an array, and you want to find out when for any given subarray, that's the query, for any given L to R of big A, I'll say, you want to find out if f of A equals g of A. And f of A is the number of steps, number of adjacent swaps to sort. And this is number of the same thing, but 1 where you have like x sub I plus 1, x sub I plus 2, and then this goes to x sub I plus 2, x sub I plus 1, x sub I. I had another idea which worked, but was so complicated it was not possible to use it for queries. Huh. It was a very precise idea to have. I mean, I don't know. I feel like I'm at the stage where I'm like, no, this is like provably correct. I just am confused on the implementation, and there's probably, I kind of assume there's an I somewhere instead of a J. But okay, so G of A is number of operations where you get to like swap, like 2, like a distance of 2, and f of A is just where all of your swaps are that. And G of A, you get one of these. So my thought is the only time where G of A is going to be the same as, the time where G of A is going to be different than f of A is if you ever have ijk, where A at I is that, but I is less than J is less than K. It's called denial. Okay, so therefore all you need to find is if you have your interval, is there any A at I, A at J, A and K, where I is less than J is less than K, A at I is greater than A at J is greater than A at K. Yeah, no, I think I don't know. I'm actually very confused on why this fails, except I'm not, because it seems to happen quite a lot where there's like a random no or there should be a yes. But anyway, so then I'm like, okay, we'll just look at every J and be like, where's the nearest thing before it that's greater than it, and where's the nearest thing after it that's less than it? And then you just say, okay, well, for the beginning bound of every like minimum envelope, right? Like I'll call this an envelope, is like, if these 3 things are included, then you're golden. So for every single left bound, like take the prefix minimum. So maybe there's some other A at J1 right here, where like it points to I, but it points to like K minus 1. Then you would say, okay, you also have this bound, which means like when you get to here, the prefix minimum is going to lower that in. Yeah, no, it's like solved. Like the entire thing is here. So I say, instantiate left bound, right bound. C is like the prefix. I legitimately, it's like spot the bug. I don't know where the bug is, and I'm very certain that this would just work otherwise. Okay, and then input X, you have a monotonic stack. You say, while the thing at the top of the stack is greater than X, or if there is something at the top of the stack that's greater than X, that's the first thing to the left of it that's greater than it. So set B at I at 0, set the left bound of the envelope to that, stack.top.second. While there's anything in the stack that's greater than X, the right bound of that thing is I. So set the right bound of that thing's envelope to I. Now you set all of the right and left bounds with this monotonic stack. I set A at I to X, it doesn't really matter. Okay, for all the intermediate J values, you're trying to do both in one loop. Yeah, I mean, are Are you sure about this? This seems risky. Yeah, I mean, maybe you can't do it in one loop, but like, why not, right? In my mind, the only risk is if you had to deal with greater than or equal to, or if it was like, okay, there's greater than, and then what you're leaving behind is less than or equal to, then there's a lot of danger there because you're going to confuse less than or equal to with less than. But I don't really think it matters if it's just purely greater than or less than because it's a permutation. But I guess that's a thing to try. I mean, maybe there's some error laden in here. I don't know. Okay, so get the left and right envelope for every j. I could say like I and k for every j. If there is an actual thing before this that's greater than it, then the bound at that is the minimum of the bound at that, and the earliest thing after this that's less than it, which could be the end of the array. That's the default. In which case, like, that doesn't affect anything. Okay, and then take the prefix minimum. And then for every element, say, is the earliest right bound occurring after the left bound of this subarray, before the right bound of this subarray, or after the right bound of this subarray? And as far as I'm concerned, this just like works. But I guess I could split this up into two monotonic stack traversals, like a backwards and a forwards one. I don't see how that really like changes it at all. But maybe I mean, that doesn't mean it doesn't change it, I guess. Like, I'm at a point of second guessing myself that's probably the next thing to try. So I guess I'll do that. So I'll say for I from 0 to n, let's move the stack down here. Okay. I'm literally going to do 3 traversals. I don't care. Okay, set a at I to x. For everything in the stack, I'm not going to set b at I here. I'm just going to set b at j at 1. So I'm saying, okay, while anything on the stack is greater than this, pop it, set its right bound to be this. Can I do this? Does that work? No. Can I say like stack.swap null or something? No, I don't think I can do that. I'll say stack.swap stack pair int. Okay, now it's empty, I believe. Damn, fuck that. Okay. It's going to be very similar for int I equals n minus 1. I is greater than 0, greater than or equal to 0, I minus minus. Int x equals a at I. While not stack.empty, so while the stack has anything, and also stack.top.first is less than x, this is saying you're going backwards now. Now the stack is going to be monotonically decreasing, so anytime there's anything on the stack that's less than this, its left bound is now this. So b at j at 0 equals I. Okay, this should be exactly the same except 3 passes instead of 1, but maybe something changes, I don't know. So I'm actually going to copy this, and I'm going to see Does anything change? Okay, well, that's because I changed it a bunch. And I want nothing to change. So that's good. Nothing changes, which is good, because that means that it is consistent so far as I can check here. I want nothing to change except the 29th test case. So I guess, I mean, for me, that's the exact same logic, but, you know, I guess if I'm debugging and I really don't know where to start, it's probably a good idea to just, like, make it more understandable. Interesting. Why would this work? That's so interesting. So I think what I'm going to do is I'm going to say, I kind of want to ask, like, I don't think GitHub Copilot is going to know. It's going to be confused, but no, I don't really care. I don't want to ask it right now. Okay. Oh, there's something there. That's interesting. Can I duplicate this? Okay, tree of endnodes, k zeros. It's going to be very similar to this. I think exactly the same, except for the knapsack at DP. Yeah, it worked, and I'm legitimately confused why. I literally just made it be 3 passes instead of 1. There's some sort of inscrutable difference between having 2 monotonic stacks go backwards, like having them go either way, versus having 1 monotonic stack. I just don't see why. Like if you have something, let's say your element is here, your current monotonic stack is there, right? You're gonna say while this, pop it off. Then it really was this portion that was the problem. Yeah. So in my mind, I'm saying, okay, well, if you have some monotonic stack, your current element, you're going to have like all of the things where there's been nothing after. You're going to have a monotonically increasing stack. So you say, okay, well, appoint this to be the first element to the left of this that's greater than it. Pop everything off the stack till your new monotonic stack is there. And for all of these elements, this is the first thing to the right of it that's smaller than it. I think I know where the problem is. It's right here when you say for everything else, set its right bound to be this. Because you might have had, like, this is your monotonic stack, but it might have like copied an array that's something like this or whatever. Right? So that means like for here, you don't want to just set it to there. You would have already set it potentially. Okay, that's what it is. Okay, so this is the same, except it goes up to 10 to the 5th. So everything's the same. Get the array. No, this is a different problem. Get the array. Get the min depth. DP, though, now is not 1001. I think it's going to be that. And now what DP represents is if you took this sum, what's the maximum number of elements that add to this sum? And then what I'm looking for is the maximum number of elements that sum to at most k. Right. The way I set this up was pretty basic. I just had recursive DP and I said add 1 whenever you add something to the O bucket or the Z bucket. I gotta text this person back. So this makes sense to me. This is very conceptual. This is DP at I at J represents, or at I at Z, I guess, represents at the given index in the array when you have Z zeros left. This is the best you can do. But now it's kind of different. Now I'm saying DP is no longer like a big 2D table, which actually is like simpler than like a 1D array kind of. DP now is just best you can do with some less than or equal to I. And best you can do means like most elements. But then it's a little bit confusing because like, okay, you're saying most elements in the Z bucket, but then what about the O bucket? You haven't really optimized that. Although I think you could just say, yeah, this is for E2. I think you could just say, I mean, maybe you could say it's not really the best you can do. Part of me almost thinks you could just say, can you have this sum? Because in my mind, the conceit of the original problem, I mean, I haven't even like tried to explain it all, but I guess the gist of the problem is you have some big tree. You're going to color some of these with a 1 and some of these with a 0. And you have some Z amount of zeros, which entails like there's an O amount of 1s that you have. Question is, if you color them optimally, what is the longest common subsequence between all nodes? which sounds complicated and then is immediately reduced to something that's not that complicated. Because if you imagine like this was your tree, what's the longest common subsequence between all nodes? Well, whatever's going on down here, you don't really give a shit because you just have like the longest common subsequence has to be with this. So it's never going to be, or it's between all leaves, sorry. It has to be with this. So therefore the longest common subsequence is either going to be a length of 1, where everything has to share at least the root value, or 2, if you're able to color this the same as like these or something. And then you'd say like, okay, well this is a 0 and these are 1s, therefore you're good. So that's the first like observation, is like the longest common subsequence is only going to be as long as the depth of the shallowest leaf node. So if you had like that, then immediately you're only looking at 1, 2, or 3. And then the second thing to realize is it's kind of like the quote unquote, in my mind, the like cost of assigning all of the nodes to have the same value. Like you would always want to count the root in the subsequence. And then the question is like, okay, well, what if you had the root and then also like this and you aimed for 2? But it's like, why would you color all of these 0 when you could have just colored these 3 0? And then all of these get that if we get rid of this. So the idea is like you would want to, you always want to try to aim to color the fewest nodes possible in a layer in order to align the subsequences of everything below those nodes. In other words, like you're never going to color all of this or all of this when you have this available. Or like if there was like that, you would always choose to make these be the same color to get this like extra +1 to your maximum before you're like down here trying to get all these to be the same. So then the problem really has been reduced to not longest common sequence between all leaf nodes, but longest common prefix between all leaf nodes. So then the question becomes like, how far down can you go by assigning all of these to be 0 or all of these to be 1 before you have some situation where you have like 2 0s and 3 1s and you can't assign all these to be one of them. And then that's just kind of like knapsack DP. So that's what this code is doing. It's saying like, you're at some index, aka some layer. There's going to be a certain number of nodes you just have to assign. So here you could kind of change this into an array where you could say array is going to be 1, 2, 3, 5, 7. Because you have 1, 2, 3, 5, and 7. Yeah, 7 nodes per layer that you would have to color to be the same, to be contributing to your answer. And then it's just sort of like, okay, well, you have some amount of Z, some amount of O. You could just do regular O on knapsack DP. But you can do better than that. Classic Aphex Twin. So I also, though, kind of am thinking that there's the optimization that, like, if you have, let's say, Z equals, like, 12, you're purely asking not just, okay, well, what's the best I can do? How many nodes are there total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, there's 1 plus 2 plus 3 plus 5 plus 7, so 18. So that means that 12 of these are going to be a Z, and 6 of these are going to be an O. And in my mind, you only ever are going to have at most a single row that is not uniform. Like, there's no reason to have a fracture there and a fracture here. No matter how you, like, if these are all zeros and these are all ones, no matter how you split it, you would always be able to change it so that there's only at most a single row that has all zeros and all ones. So with that in mind, immediately you know that your answer is either going to be, if we say m is like the length of the shortest path to a leaf node, so like m equals 4 in this example, you immediately know your answer is going to be m or m minus 1. And it depends on whether you can or can't exactly sum to 12, or I guess exactly sum to 6. Right? I think it's still n root n though. It doesn't matter. That's not really going to change anything. So I think the idea behind n root n, you need square root decomposition. So let's say like z equals 20, o equals like 50. And then our array is like 1, 3, 12, 13, 16, 40. I don't think that this could ever be possible, but let's see, we have 4, 16, 29, 45, 95. Let's add like 45 here. So we got 140, so these need to change. Let's say we just have like, I don't know, 60 and 80. Okay, and then we know n is equal to 140, and z plus o is going to be n, because everything has to be colored at least as a 0 or a 1. So the idea here is we would say, okay, everything above the square root of 140, which is going to be everything above 12. I guess let's change this a little bit and say, everything below the square root of 140. Wait, no. Let's say 145, 151. Just to make it be exactly 144. Everything above this, you can kind of say, no, I don't care about this. This is where I think the square root decomposition is kind of different. Because I feel like usually you draw a partition and you say, I'm gonna grab some water. So I feel like you usually draw a partition. Oops. But I think instead what you could say is the length of the path to the shortest leaf node, that's going to limit the actual nodes you care about. You never care about coloring any of these. So therefore there's like a separate n that you care about, which is that. So I'll call this like m. And then the real n Or no, yeah, let's say n is this. These are like all the paths that I kind of care about. But there's going to be some other n, and let's say this is like 1,000. And that's like, there's other stuff below the leaf nodes that I don't care about. But I know that this is going to be less than or equal to 2e5. But I could say, take all of these, I know for a fact that there's only going to be root n distinct elements here. So I bucket these, so I'd say, okay, this, there's 2 of them. Here, there's 1, there's 1, there's 1, and so, well, there's only 2 left. You bucket them, and then with each of these, then you can have O of n per I'm using my new washing machine for the first time and it is flipping out. I kind of want to make sure it's okay. Washing machine. I can take O of n for each of these, but then I need to account for multiplicity. So I took a walk and I was like, I feel like you can use a sliding window maximum for this. Yeah. So this is out the window. That's out the window. But then what am I really saying here? I'm saying the most elements that sum to exactly a given number. How is it helpful? I guess that's where, like, I see this as the optimization for O and knapsack DP, but it's hard for me to put into this context because you would only be optimizing for Z or O. But I feel like you could just say, where am I? either you will be able to have an exact split between the ones and zeros, or you won't be able to have an exact split. And so it's purely just, are you able to reach a given element? Does this even make sense? Yeah, I think this makes sense. DP is out the window, pref is fine. That's all fine. I guess I just gotta go for it. So DP gets filled. I don't even think I really need that. I think I can have DP be like a bit set. Except DP is 0 is 1. I'm going to have a counter. The counter is going to have each element and the number of occurrences. Okay. Okay, I want for the offset from 0 to x, how does this work? Does this work? Or is this logarithmic? No, I think this doesn't work. No, this could work. For int I equals O, I is less than or equal to n, I plus equals x. XF, kind of want another one. It's just a buffer. Cur plus equals dp at I. if R minus L is equal to the frequency, that means you need to increase the frequency. Too much going on. Just gonna say R0 ISO is this and that. Okay. Let's see. So if you had two elements, you're saying I'm here. I could either go 11 back and then I added one 11. Or another 11 back and I added two 11s. So this would be R equals 0, R equals 1, R equals 2. So if R is greater than F, then you need to remove this. I minus X, times F. Right? Yeah. dp at I or equals cur is greater than 1. So I'm saying, is this reachable if you use up to f of x? Okay, for every offset, so this sliding window should be ov n root n. Okay, now for res is going to be m if dp at, I think I just want to say in 0 is equal to k, 1 is equal to n minus k. If dp at 0 equals 0 and dp at 1 equals 0, then res goes down. Two 1 5 1 1 3 2 5 1 2. One 1 2 2 3 3. So it's saying 2 and 3 go to 1, 4 and 5 go to 2, 6 and 7 go to 3. So it's a perfect binary tree. The answer, I guess, shouldn't be 2, it should be 3. There's 3 zeros, which means there's 4 1s, which means dp is not doing the right thing. It says there's a 0 and nothing else. I assume this should go through a bunch. Yeah. This should say there's a single 1, a single 2, and oh, weird. And there's a million of that. Oh, I see. The 1, the 2, and the 4 is right, though. There's a single 1, a single 2, and a single 4. So cur should definitely have stuff in it. Yeah, it does. X times F. I think I want it to be that. No. So this is true. If you're at 4, 1, 2, 3, 4, you're saying I do want to include this. Yeah, okay. Okay, cur has stuff in it. Oh, cur greater than, what am I doing? Cur greater than 0. Zero, 1, 2. Okay, almost. This is saying you have access to a 1. This is saying you have access to a 2 now. Four, 0, 1, 2, 3. n. Zero, 1, 2, 3, 4. Hmm. Zero, 1, 2, 1, 4, 6. Okay, 1, 1. Hmm. 3, 0. There we go. DP at Z0 or DP at O. Okay. Three, 2, 5, 1, 2. 2, 2, 2, 3, 2. Hmm. Expected 2, found 1. Let's see, you have to add up to exactly it, but you don't care if that's not the constraint anyway. If max of Z and O is less than M, that means you have some sort of tree. And if you just had more than that for both of these, you wouldn't care. If you had less than that for one of them, you still wouldn't care. You need less than that for both of them. And then you would care. Three, two, five, two, two. Two, five, one, two. 5 and 2. They all point to there. No, I don't want M. I want the number of nodes below M. The number of nodes. Goddamn. A at depth plus plus, so A. So I want prefix at A plus M minus 1. Oh no, not A. Just prefix at M minus 1. What the fuck? So it's probably prefix at M, because it's probably 1 indexed. 32522. Interesting. Hmm. I think I gotta restart this. One, two, three, four. Hmm. Two, but it should be three. One, two, three, four. This is it. Oh, wait. Oh. Huh? Okay, we got 5. Okay, that should not be going through. Z and O, well, no. They're both 5. Damn. I guess my plan didn't work. I have to think about this one. It's crazy you made it through 9 test cases. I guess you have a buffer of 3. So really you're looking within 3 of that. If it was 0, you would need to exactly add up. If you had 1 extra, you'd say, okay, it can be off by 1, so this would work. So I guess I could just BFS out. For I from 0 to this number, that number is going to be n minus ref at m if Yeah, we're gonna go in 1 minute. Let's see. Z minus I is greater than or equal to 0, and dp at I equals 1. You found something. Same thing with O. Same thing with plus. Is it less than or equal to? Less than or equal to. Oh shit. Let's grab these, compare. 4, 2, 2, 3, 2, 3, 4, 2, 2, 2, 2. 4, 2, 2, 3, 2, 3, 4, 2, 2, 2, 2, a bunch of 2s. 3 3s, 2, 2, 3, 2. Uh-oh, I have a 1 in there. No. Well, no, that might just be that there's not 30 test cases. Like if I said like, yeah, because each of these is 4. So if I said like 300, it'd probably end in a bunch of 1s. Yeah. Phew. What? 22411. That's not right at all. That's not even close. So I'm guessing it's going to say 214111. It's going to be 10101. 10111. Oh no, that makes sense. So it's 3 zeros, 4 ones. Okay. So it should correctly see immediately you could arrange it so that you can fill up the zeros or the ones, it doesn't matter. DP should be all ones. I don't see why it wouldn't be. Okay, all ones, so that's fine. I equals 0. I goes up to n minus pref of m, which is just 0. I see. So it's exclusion is not just by default equal to 1, because you could have a scenario like this where there's nothing left over. You're going to have to set every single thing equal to 0 or equal to 1, and then you're going to have to split it into like a 3 and a 4 or a 1 and a 6 or something. But mine, the loop is where it should figure out like, oh, okay, you can do that. And in theory, it's more lenient than the previous way that I had it, where this isn't possible. However, now, if there's no loop and there's nothing extra, you still want to just check initially, like, well, do I even need something extra? So this isn't by default 1. Let's do that. No, that's weird. So this is going to be dp at O equals 0 and dp at z equals 0. Do 2, 5, 1, 2. Okay. Let's try that at 15. Get these test cases. See if they work. 4, 2, 2, 3, 2, 3, 4, 2, 2, 2, 2, a bunch of 2s, 3 3s. 4, 2, 2, 3, 2, 3, 4, a bunch of 2s, 3 3s, and then a 2. Okay, so these are the same. And that's the same. Oh my god, monster problem. If this doesn't work, then I'm just out. Fuck, it doesn't work on 3. That made it less far? No, I know why that didn't work. No. Okay. I gotta go back to the drawing board. 6th numbers. 1, 2, 3, 4, 5, 6. Expected 1, found 2. So it looks like that. I don't see why this wouldn't be 2. You could say color all of, no, I do see why this couldn't be 2. Okay, well, there's an easy fix for this. But I'm definitely getting to the point that just like I'm just randomly resubmitting. I'm gonna try one more. Min of A at M minus 1 ref of M. Should say 1 now. Nope, it says 2. Alright, I'm gonna have to incubate on this one more. Thanks for watching.